All right, now we just went through uh, and had presentations for project number 1. Um, Next week on Tuesday, I'll pass out your second projects, or actually, I'll make them available for cohorts to fight over to make your choices. Notice you're only going to have about 2 weeks to work on them, okay? But now you've got your cohorts formed. You've got your synergy. You've learned how to use some presentation technology, or maybe not so much, but hopefully you will learn between now and then how to put together a good PowerPoint or whatever other PowerPoint or presentation media that you would like to use for the future. Okay, what we're going to talk about tonight is the doing double integrals over the plane, right? Over two-dimensional regions. But this time we're going to be converting to polar coordinates. You might have come across some double integrals that were pretty hairy, huh? But if you are integrating over regions that could be, it would be better for you to do a substitution using polar coordinates, and so be it. You'll see that some of these integrals will definitely become much more simple after doing that substitution. So remember what polar coordinates are, right? Remember, let me just go off to the side. Remember that x is equal to r cosine theta, y is equal to r sine theta. So I'm trusting that you remember what polar coordinates are and how you can convert back and forth between r and theta and x and y. Okay, so here's kind of the idea here is, from 14.1 to 14.2, we were thinking that that the volume under the surface could be calculated by integrating this function z equals 9 minus x squared minus y squared over this region on the xy plane. It's a circle, right? So how you have to set up your double integral is you have this region on the xy plane that's given by x squared plus y squared equals 9. So you would have to solve for y, and y is equal to plus or minus square root of 9 minus x squared. And so you see what your limits of integration for the y variable will be involving those radicals, right? And so it gets to be a little bit algebraically messy. Well, it turns out to be that if you replace x squared plus y squared by r squared, and then you have just r equals 3 as the equation for the circle. And it turns out the integral in polar coordinates is just a whole lot more simple. So calculating the volume under that surface and above the xy plane turned out to be much more simple using polar coordinates. So that's kind of the motivation here. It turns out that sectors, all of the different flavors of sectors, are what are known as polar rectangles. Now, what do we mean by polar rectangles? Well, on the in the Cartesian coordinates x and y plane, that the rectangle is such that the variable x varies between a constant value and another constant value, and the y-coordinate varies between two constant values as well. Well, in polar coordinates, we have the same thing for the two variables. We have that the radius varies between two constant values, like between 0 and b, for example, and theta varies between two constant values, like 0 and pi over 2, like you see here, like you see there, like you see there. All of those are polar rectangles. Just like integrating over rectangles on at x and y coordinates is pretty simple, right? Well, it'll be the same thing for polar rectangles when we're dealing with polar coordinates. So let me just kind of give you just a rough discussion as to how the dA element is formed in polar coordinates. Now, before we do that, let me just remind you of how we did it with X and Y coordinates. Remember, we chopped up your region on the XY plane into a bunch of rectangles, and each rectangle, let me blow up one of these rectangles, was delta x by delta y. So each element was dx dy when you take the limit of x and y, delta x and delta y go to 0. So dx dy, dy dx were the two dA elements for your rectangular double integral. But what is it going to be for a polar double integral? Well, here we've got some sector, some region on the xy plane. Actually, it's on the polar plane now. But instead of having rectangles, we've got these polar rectangles now that we've sliced and diced our region on the xy plane. We have these little delta r's and our delta thetas. Now, what is the area of this little sector here? Well, how do you calculate the area of a sector? Remember that? Well, let's see here. There should be a formula somewhere. How do you calculate the area of a sector? Well, in some of your textbooks, they show this picture here. How to calculate the area of a sector. It's going to be the area of 1/2 times radius squared times angle theta. So now what you're thinking about is finding the area of the big sector here minus the area of the smaller sector. And the result is the area of that yellow thing right there. Does that make sense? So using 1/2 r squared and times the difference of, well, I'm sorry, 1/2 times the difference of the r squareds times delta theta is what's going to give you the formula for the area of that yellow thing right here. So here's the blow up of that yellow thing, of that polar little small rectangle. So here's the big sector that goes from the pole out to here. And what is the area? So here's your delta theta. And maybe you can go up half a delta r, half the delta, down half a delta r and stuff. And then you can use those formulas for areas of sectors. So, and if you were to look about almost completely down at the bottom of page 1006, in fact, I could do this right in here because I've got my tablet PC up and running, is that your delta A sub k, which is the area of this yellow thing, is going to be given by this, but where did that come from? Well, it's the area of the big sector minus the area of the smaller sector. Now, the area of the big sector is 1/2 times that, what they call r star sub k plus the delta r over 2 squared, and then times delta theta. That's the area of the big sector minus the area of the smaller sector, which is r star sub k minus delta r over 2 delta theta. And there's a square on that binomial there. So you just multiply it out, collect like terms, simplify, and that works out to be this r delta theta. And of course, then take the limit as delta r and delta theta goes to zero. I mean, and then boom, that's what we have. So r d theta is your dA element. R is going to vary between A and B. Theta is going to vary between alpha and beta. And that's when you're integrating over a polar rectangle. And of course, you're going to have your function, your integrand, expressed in terms of polar coordinates. R and theta. So let's just jump into an example. Find the volume of the solid bounded by the paraboloid z equals 9 minus x squared minus y squared in the xy plane. And here's the picture. We already saw a picture of this earlier. Here's z equals 9 minus x squared minus y squared. Remember, x squared plus y squared is equal to r squared, so you have z equals 9 minus r squared expressed in terms of polar coordinates. Now, when z is equal to 0, r squared is 9. That means r equals 3. R equals 3 is the equation for the circle on the xy plane. That's this circle right here. So this is the circle that you're actually going to integrate over, where r is going to go from 0 to 3, theta is going to go from 0 to 2 pi. So your integral is going to be integral, and 9 minus r squared, and r dr d theta. dr d theta. Remember, r goes from 0 to 3, theta goes from 0 to 2 pi. Common mistake, folks, is to forget about this r right here. Make sure that you fold that into your integrand. So now you have the double integral of 9r minus r cubed dr d theta. Now this is just like any other double integral that you've done before. Integrate with respect to r first. So what do we have here? We have 9 halves r squared minus 1/4 r to the 4th, 0 to 3. We have d theta out here. Now plug in 3 for r. You got 3 squared is 9. Get 81 halves minus 1/4 times 3 to the 4th. Now 3 to the 4th I think is 243. And then of course you don't see any mention of theta within that integrand, do you? So you're just integrating a constant with respect to theta, huh? So you just multiply by 2 pi. So what does that work out to be? So that works with 81 pi over 2, I guess. Okay. So any questions on how to do that? It's just a double integral. Just a special sort of double integral, but at the end of the day, it's still a double integral using polar coordinates. All right, let's move on to our next example, number 2. Region bounded by two surfaces. Find the volume of the region bounded by the paraboloid z equals x squared plus y squared, and z equals 8 minus x squared minus y squared. So let's go ahead and take a look at those two surfaces. And we need to find the volume encased between these two surfaces. So here's a picture. It's always nice to see these beautiful pictures produced by the publisher. But even if we didn't have this, we could generate these by using some sort of computer algebra system like Maple or Mathematica or MATLAB or Derive or many others out there. Even on the internet, there's three-dimensional surface plotters. All right, so, well, the big thing that you're going to need to do is figure out what your limits of integration on the xy plane are going to be. So figure out where the two surfaces match. So you set the functions equal to each other. Set 8 minus x squared minus y squared equal to x squared plus y squared. And what do you get? Yeah, you set 8 minus x squared minus y squared equal to x squared plus y squared. So you have 8 is equal to 2x squared plus 2y squared. That means 4 is equal to x squared plus y squared. And remember, x squared plus y squared is r squared. So that means that r is going to be equal to 2. So that's why you see that circle of r equals 2 down there. So that's going to be the region that you integrate over. And then you're going to be integrating over, or you're going to be integrating the function, which is the difference between this function and this function. Yeah, this. So your volume is going to be integral, and the difference between those two functions is the upper one was the 8 minus r squared minus that bottom one, which was r squared. And then remember the dA element is r dr d theta. Man. Oops, let me fix that. R dr d theta. Remember, r is going to go from 0 to 2. Theta goes from 0 to 2 pi. So simplify the integrand. Have 8r minus 2r cubed dr d theta. And integrate with respect to r. And remember, this integrand does not involve the variable theta, so you could just take the difference between the upper and lower limits, which is 2 pi, and multiply by that. And you have what? The integral of 8r is 4r squared. The integral of 2r cubed is, what, 1/2 r to the 4th. Evaluate from 0 to 2. From 0 to 2. 1/2 r to the 4th. Thank you. Yep. And then you'll plug in 2 for r. You got what? 2 squared is 4 times 4 is 16 minus what? 16 over 2, which is 8. So 8 times 2 pi is 16 pi if we did this right. So that's the volume. That's the volume between these two surfaces. All right, let's do another example here. We're going to find the volume of the region beneath the surface. Z is equal to x, y plus 10. Above the annular region, r is equal to r comma theta, such that r is between 2 and 4, and theta is between 0 and 2 pi. Let's go ahead and take a look at the picture of what's going on here. Here's the surface, the graph of xy plus 10. and we're going to integrate that over this annular region where r is between 2 and 4, and theta goes from 0 to 2 pi. We're going to find the volume that's below the surface and above this annulus. So that volume is just going to be integral of this function, but remember x is equal to r cosine theta, and y is r sine theta, and then plus 10. So that is the function that we're integrating times r d r d theta. Remember, r goes from 2 to 4, and theta goes from 0 to 2 pi. So again, you take this integrand and you multiply it out, simplify it, integrate with respect to r, evaluate between 2 and 4, and then integrate with respect to theta, and evaluate from 0 to 2 pi. And what does that get you? And that works out to be 120 pi. I'll let you check the details. They're in the textbook. Okay? But, of course, you're not always going to integrate over polar rectangles, huh? You need to be able to integrate over any other polar regions on the plane. It could be that r, as in the distance between the pole and the curve, it could be that r really is a variable function with respect to theta. Or you could take the equation that governs that polar curve and solve for r in terms of theta. So you could have a polar region that looks like this, where you have definite limits for theta, but r is going to vary between this lower curve and this upper curve. So it's just a matter of figuring out what are these two curves and what are the limits for theta. And so what you're going to be having for your limits of integration then is r is going to vary between this function down here for your lower limit, function of theta, and this upper function for the upper limit with respect to theta, and then you have your constant limits for theta. Now, I have seen some polar integrals where you would have theta as a function of r, and then you have constant limits for r. Not very common, though, but you could do it. But I think all the problems that we're going to do really involve just that sort of situation where r is a function of theta, and theta varies between two constant values. So that's basically what we're talking about here, is that you have these variable limits for theta, for r, I mean, variable limits for r, functions of theta. So let's go ahead and dive right into an example here. Example number 4. Now, we're going to write an iterated integral for the following regions on the xy plane. The first one is the region outside the circle, r equals 2, and inside the circle, r equals 4 cosine theta. So what we want to do is find, or at least set up an integral that will calculate this area right here. Okay, so the big thing that you want to be able to do is, if you don't see the graph, for you to be able to sketch the graph. And then find, your outer function, your inner function, and your limits of integration. So where do these two circles meet? Well, of course, here it says negative pi over 3 to positive pi over 3. But why is that true? Well, you set the functions to equal to each other and solve for theta, right? That's what we always did in algebra class, right? So you set the two functions equal to each other. 4 cosine theta is equal to 2. Because remember, the one function is 2 and the other function is 4 cosine theta. So now solve for theta, divide both sides by 4. So you get 2/4, which is 1/2. And cosine function is 1/2 when theta is equal to negative pi over 3 and positive pi over 3. Okay, so there. You have to do a little bit of trigonometry and algebra to solve for your limits of integration for theta. So theta is going to vary between negative pi over 3 and positive pi over 3. R is going to vary between 2 and 4 cosine theta. Okay, did everybody see that? So for part A of example 4, to set up that integral which calculates the area, of course you integrate the function 1 to find the area, but it's just really a matter of what are the limits for r and for theta. Remember, r went from that circle r equals 2 out to the circle 4 cosine theta. And then theta went from negative pi over 3 to positive pi over 3. And that's what that area, that's what this area was. Remember, r went from 2 to 4 cosine theta. And theta went from negative pi over 3 to positive pi over 3. Any questions on that one? And then for part B, they want us to find the region inside both circles of part A. So let me just show it this way. It's really this right here. It's this white area right here, which would be kind of like the complement of the yellow piece. But it's this part right here. So it's actually going to end up being 3 integrals, which calculates it. Actually 2 integrals because you can use symmetry. If you know this area right down here, then you could double it plus to get this sector as well. So, but there are 3 regions that you need to find the area of. This region right here, this region right here, and then this region right here. Now this region right here, you're going to integrate from negative pi over 2 to negative pi over 3, from 0 to the black curve, which is 4 cosine theta. Okay, so and that's what they're talking about right here. So this little shaded region right here. So this area, see if I can write a small double integral r d theta. R is going to go from 0 to 4 cosine theta, 0 to 4 cosine theta, and theta goes from negative pi over 2 to negative pi over 3. And then you get this region right here, and you're integrating the function r equals 2 from negative pi over 3 to positive pi over 3. So write a small little integral here. So r goes from 0 to 2, theta goes from negative pi over 3 to positive pi over 3. And of course, this region you're integrating 4 cosine theta, which is this one right here, on the interval from pi over 3 to pi over 2. So write a little small integral, r d theta. R goes from 0 to 4 cosine theta. Theta goes from pi over 3 to pi over 2. Okay? And then you just add them all up. What you could do alternatively is you you could use symmetry to your advantage because of the fact that this area down here below the x-axis is the mirror image of this area up here. You could just find this area right here. Everybody see what I'm talking about? This area here, plus this area here where you can integrate from negative 3 to 0, and add up those two integrals, and then you'll have the whole region. This whole region, okay? Either way works fine. Any questions? The hard part, folks, of course, is getting your limits of integration correct, and make sure that you're integrating the correct function over the right interval. So you practice that. So what we were doing is we were finding the area of polar regions just by integrating the function 1. Okay? So if you just need to find areas of polar regions, just integrate the function 1, r d theta, over appropriate limits for r and for theta. Let's do another example here. Example number 5, area within a lemniscate. Compute the area of the region in the first and fourth quadrants outside the circle, square root of 2, and inside the lemniscate, r squared is equal to 4 cosine 2 theta. All right, so here's a good visual of what it is that we need to find. This area right in here. So, of course, it's always nice to see a graph, but you could use your graphing calculator or your computer to graph these for you. So we're talking about this yellow region right here. Outer function is going to be the lemniscate, and the inner function is the big circle, right? So you take that equation for that lemniscate. Remember that was r squared is equal to what? 4 cosine squared 2 theta, and just take square roots. So you get this thing for r. And then to find those limits for theta, you set the two functions equal to each other. You take what? This function, set that equal to this function. So you have square root of 2 is equal to 2 times the square root of cosine of 2 theta. Do the algebra to solve for theta. Maybe divide both sides by 2. So you have what? 1 over square root of 2 is equal to square root of cosine 2 theta. Then square both sides. So you got 1/2 is equal to cosine 2 theta. And the cosine function is going to be equal to 1/2 where? Well, when the angle is plus or minus what? Pi over 6, right? Pi over 3, right? Plus or minus pi over 3 is equal to 2 theta. So that means that you divide both sides by 2, you get plus or minus pi over 6. And that's what gives you your lower and upper limits for theta. Everybody see that? So now you've got your limits for theta, you know your limits for r. So r is going to go from square root of 2 to 2 times the square root of cosine 2 theta, which is that one. And theta is going to go from negative pi over 6 to positive pi over 6. So that area, so we'll just integrate r d theta. So r goes from square root of 2 to 2 times the square root of cosine 2 theta. And theta is going to go from negative pi over 6 to positive pi over 6. All right, again, that's a perfectly simple double integral for you to solve. And I'll let you check the details. But it's like any other double integral that you've done from like 14.2, for example. except instead of x and y, you're using r and theta. So that works out to be square root of 3 minus pi over 3. Okay? Moving along here. Do you remember how to calculate average value? Now, if there was a single integral, you would just integrate the function over the region and then divide that definite integral by the length of that interval. But when we are doing double integrals, then what you do is you divide by the area of the region that you're integrating over. Okay, and that's how you calculate the average value for your double integral. So you might have to do two integrals, one integral to calculate the area that you're integrating over, and then your second integral to actually integrate the function over that region. So be on the lookout. I think you got one or two problems on the homework where you'll be asked to calculate average value. So number 6, find the average value of the y-coordinates of the points in the semicircular disk of radius A, given by r is equal to let's see, r goes from 0 to A, and theta goes from 0 to pi. So we're talking about a half circle of radius A that you're integrating over. This is going to define your limits of integration. But what is it that you're actually integrating? You're integrating the y value, the y coordinate, I mean. But remember that y is equal to r sine theta. So you're going to integrate y, in other words, integrate r sine theta over this region here, and then divide by the area of that region. This region is a semicircle of radius A. So, first of all, that area is half the area of a circle of radius A. So your average value is going to be 1 over 1/2 pi a squared times the integral of that function. The function that we're integrating is r sine theta. And then times r d theta. Now, your r is going to vary from 0 to a, and theta is going to go from 0 to pi. All right, so hey, it's a double integral. Integrate with respect to r first. Remember that your integrand is r squared sine theta. So you integrate with respect to r first, and then you integrate with respect to theta first. I'll let you check the details, but this whole integrand, this whole integral, including the 1 over the area, I guess that works out to be 4a over 3 pi. Go ahead and work through the details. As we go through the semester, I leave a lot of details out because I'm assuming that you can look them over in the example or work them out in detail yourself. Okay. Now, I've got a question for you. Do you want to push on into 14.5 for the last half hour, or do you want to save that for next time? Next time? Because what we could do is we can lump this triple integrals in 14.4 together with the discussion of 14.5, which is still triple integrals, but this time using cylindrical and spherical coordinates. All right, so what I want you to do, besides studying for the test, of course, next Tuesday, is I want you to review cylindrical and spherical coordinates. Now, let's take a look here. There should be a discussion somewhere about those coordinate systems. Do they give it? Let me just take a look here. Okay, yeah, they for this textbook they actually give you a good discussion at the beginning of what cylindrical and spherical coordinates are. In other textbooks, they have the discussion of those two coordinate systems earlier in the textbook. So unfortunately, we oftentimes would have to take a step back and go back to that previous section to review that. But no, it's a good thing that they actually talk about those coordinate systems. Well, look, we know the XYZ coordinate system, right? So a little chunk in three-dimensional space is delta X, delta Y, delta Z. But imagine two other coordinate systems, like a cylindrical coordinate system that involves basically polar plus the Z coordinate system. So it might have a little sector together with some altitude, some vertical altitude. So you'd have r dr d theta with the dz as your d element, dv as a little piece of volume. The other one, which is more esoteric, is your spherical coordinate system, which involves two angles and a radius. So imagine that I could locate any point on the plane by telling you exactly how far it is from the origin out to that point. That would be a straight line distance. And then I need two angles, right? One angle will be the angle between this radial segment and the positive z-axis. That's one angle. The other angle, of course, if you were to project this radial element down onto the xy plane and then measure that angle with respect to the positive x-axis. So you have two angles and distance for your spherical coordinate system. So on Tuesday, we'll take the test afterwards. So we'll start off the class period on Tuesday by talking about triple integrals in x, y, and z coordinates, and then triple integrals in the cylindrical and spherical coordinate system. And then, if we have time, we might be able to talk about using integrals to calculate mass. But, I mean, that's just a simple application, so we should be able to do it. And then still have time for you to take your test. I don't think we're going to cover 14.7. That's a nice to have chapter, but I don't think we have the time. A nice to have section. But so if you wonder where the r dr d theta or the rho squared sine phi d rho d phi d theta comes from when you're doing these change of variables from one coordinate system to the next, well, section 14.7 will talk about it. And then I'm also looking forward to us to pushing chapter 15 next week, where we're going to be doing calculus. It's still in 3 dimensions, but this time we're going to be doing it in vector fields. So that's something to look forward to.
Are you going to be assigning as many problems still?
No, their homework will be tapering off. Because I don't want there to be a big log jam of problems at the end of the semester. But you got to do your part in making sure that you still continue to read the textbook and engage those problems. All right? Sound good? All right. Have a good evening, everybody, and I'll see you on Tuesday. Happy 4th of July. Stay safe. Be careful with those bottle rockets.
I assume you put it up, but.
Yes.
Hey, you said to come to your office hours in
Yeah. Well, okay. So I know that you were going to ask me. I know that you did well on the quizzes and the exam, but it had to do with the homework, and the homework is what really drug your